Today we learned about clock synchronous state machine design. Okay, from the basic structure of state machine that you already know is composed with flip-flop, next state logic F, and output logic G. So for the design, you must design all of these three parts of the circuit. Okay. For flip-flop, for state memory. For this part, it's very easy to design. You just know number of state. Okay. For example, if your state machine have four state, so you need at least two flip-flop, okay, to use for state memory. Namely, for two flip-flop, maybe Q1, Q0. That means it can represent 0, 0, 0, 1, 1, 0, and 1, 1. Okay, four state. And if your state machine have 10 state, for example, so how many bit need? At least 3 not enough, right? Because 3 can represent generally just only 8, right? So 4 bit need at least. So for flip-flop, you need 4 flip-flop, maybe Q3, Q2, Q1, and Q0. Okay, that can represent up to 16 state, but you may use just 10 state. It's okay. And don't forget that out of this, use the same clock, okay, common clock. And when clock tick, flip-flop will read the input, right? For example, if you use the flip-flop, when clock tick, input from the flip-flop will be updated to output Q for each flip-flop. And this signal is come from circuit F, right? Circuit F. And the output of this circuit F that apply to flip-flop is called excitation signal. Okay. So if you want to design the state machine, that means you must design circuit F also. And because circuit F is computational circuit, right? So if you want to design this part, you must know the relationship between output of circuit F and input of circuit F. That means you must know something like numerical relationship between output and input of circuit F. And then if you know, then maybe you may use K-map to find out equation for each output of circuit F, or excitation equation. Okay, so if you can determine excitation equation, then you can select logic gate and follow these excitation equations for each output of circuit F. And for each state of state machine, namely is combination value of Q3, Q2, Q1, Q0. For example, if you want to convert to the final output of the circuit, you need to use circuit G, output logic. And this part also is combinational circuit. So you must know the relationship between output and input of circuit G, and then maybe use something like K-map to implement this part of the circuit. So you need to derive output equation to implement this part of the circuit. Okay, that's all for the design. Okay, this is the general basic concept that you should know. Okay, now let's see example. Example 1. For this example, it is quite long because we will talk so detailed about the design. But in practical, maybe it not so hard like this example. Okay, and let's start. Okay, at the beginning, you should understand the problem. Okay, and then you plan to design. At first, you may think about the state of the state machine. Okay. At first, let's try to do this example. Okay. Example 1. Design clock synchronous state machine with two input A and B and single output Z. Something like this. Input A, input B, output Z. Okay, and maybe clock at here. Clock. Output Z will be 1 if input A had the same value at each of two previous clock ticks. Okay, or B is 1 since the last time that the first condition was true. Otherwise, the output should be 0. Okay, there are two conditions. Okay, the first condition that you make output Z to be 1 is input A had the same value at each of two previous clock tick. What does it mean? For example, this one. At the beginning, let's focus on input A. Okay, at the beginning, this condition is not true, right? Okay, because there is no any clock tick, right, at the beginning. So output Z now it should be 0, and assume is a positive edge. Then when clock tick, now clock tick, the first clock tick, value of input A is 0. Okay, that's only 1. So these two previous clock tick still be not occur. That means now output Z should be 0. Okay, still be 0 at here. And then when clock tick, okay, again, now input A is 0. So if you consider maybe point of time during this period, this point of time, the two previous clock tick is what? This point of time is this one and this one, right? A is 0, A is 0, the same, right? Same value. This point of time also. The two previous clock tick is this one and this one. So A is 0, 0. So this condition become true. That means output Z become 1. Okay, during this period of clock. And then when clock tick again, what happened? Now A is 1. A is 1, right? That means this point of time, the two previous clock tick is this one and this one. A is 1 at here, A is 0 at here. So this condition is not true. That means output Z now become 0. And when clock tick at this time, A is 1 at here, and the previous is 1 also. So after this clock tick, output Z become 1. Okay, understand this first condition to make output Z to be 1. And for the next clock tick, at here, output A is 0, the previous A is 1, so different, right? Not the same. So output Z become 0 again. Okay, this is the first condition. How about the second condition? For second condition, say that output Z is 1 if B has been 1 since the last time that the first condition was true. This means if Z is 1 and input B is 1, so output Z still be 1. Okay. For example, when clock tick at here, A is 0, the previous one A also 0. So now output Z is 1. Okay, now output Z is 1, right? And when clock tick at here, B is 1. Okay, B is 1 and output Z also 1. So output Z still be 1. Okay. Put A now. Okay. B not considered in this case. And clock tick at here again. B still be 1 and Z still be 1. So output Z still be 1. And clock tick at here. Now B is 0. So this condition is not true, right? So then must consider the value of A. Okay. Now A is 1 and the previous clock tick A is 0. Different, right? So output Z change to be 0 again. And clock tick at here. Now Z is 0. Even B is 1, not effect, right? You must consider the value of A at this clock tick and this clock tick the same. Then output Z become 1. And when clock tick at here, A is 0, the previous A is 1. So different, output Z is 0. Okay? Okay. So now from this condition, the first step, you must create something like state output table or state diagram. For the example, let's start design by state output table. Okay. For this condition, you may see that the output change just only when clock tick, so it should be more type state machine. Okay, for number of state, you don't know, so you know number, you don't know number of state variable also. Okay, now let's start. At the beginning, because we know nothing, so I will start with initial state. Okay, define this state that initial state have got logic 0 output. Okay, because at the beginning there is no any clock tick. Output should be 0, right? So, and what happened when clock tick? Because there are two input A, B, right? A, B. Okay. When clock tick, if A, B is 0, 0, okay, what is the next state? It should be initial. No, it should be not initial. Because if it's initial, what happened? If the first clock tick, read data A is 0, B is 0. Okay, let's pay attention at A. And when clock tick again, if input to be 0, 0, what happened? Now A is 0, A is 0, right? It should go to state that give logic 1 output. But if you let the next state of initial when input is 0, 0, is initial. That means if input is 0, 0 again, it's to be initial, but initial output is 0. So it is not okay. So you define some state that represent that now maybe the last clock tick input A is 0. Okay, something like this. So in this case, I define A0. Okay, A0 output still be 0. A0 means the state that output is 0 and the last clock tick, the value of A is 0. Similarly, I may define A1. Okay, the state that give logic 0 output and the last clock tick input of A is 1. So based on this meaning of the state, at initial, when clock tick A is 0, so it should go to state A0. This one also, right? A is 0. And for this one, A is 1, right? It should go to state that output is 0 and the last clock tick, the value of A is 1. So it should go to A1. A is 1, right? A1. Okay? Okay. And then at state A0. At state A0, when clock tick and input is AB is 0, 0. Now A is 0 again, so it should go to state that output is 1, right? But up to now, there is no state that output is 1. So you should define new state that give logic 1 output. In this case, maybe state OK. Okay, I define the new state. Something like this. Okay, state OK. So based on this one, now at state A0, if clock tick get input A to be 0 again, so it should go to state that give logic 1 output, right? So it should go to OK at here. This one also OK. But at A0, if the next input A is 1, so it go to the state that output is 0, right? And the last clock tick A is 1, so it should go to A1. This one also, right? A is 1, it should go to A1. And at state A1, if clock tick input A is 0, so it should go to state that output is 0, right? And the last clock tick A is 0, so it should go to A0. A0 right here. And A1, when clock tick get input A is 1 again, so it should go to state that logic output is logic 1, so it should go to state OK. This one also, right? State OK. And how about state OK? At state OK, if and the next input is 0, 0, what happened? A is 0, B is 0. Okay, let pay attention at A. Now A is 0. If this state OK is come from the last two value of A is 0, 0. So when clock tick, the last clock tick A is 0, and now A is 0, A is 0 again. So it should to be state OK, right? But if the last this OK is from A is 1, 1. The last value of A is 1. When clock tick, again A is 0. So it should go to A 0, right? So what happened? The same state, but have two possible next state for the same input condition. Now it's not okay, right? It's not okay. It's impossible. So what should you do? The problem is this okay is maybe from A is 0, 0 or 1, 1, right? That means you define okay. It's not enough, right? It's not sufficient to cover all conditions that give logic 1 output. In this case, you should define the new state, okay, to show that the last value of A is 0 or 1, right? So in this case, I define OK 0 and OK 1. OK 0 and OK 1. OK 0 means the state that output Z is 1 and the last value of A is 0 for OK 0. And for OK 1, the state that gives logic 1 output and the last value of A is 1. So in this case, there is no OK, right? So I must change this OK to be what? OK 0, right? Is OK 0 and this one OK 1, OK 1, right? That mean for this case, at OK 0, if input A is 0 again, so it's go to OK 0, right? But if at the state, now output Z is 1 and input A is 1, but the last A is 0, so we must go to A1. And at state OK 0, for the second condition, now B is 1, right? For these two cases of the input AB, so the output should be 1. And for this one, the last value of A is 0, so it should be OK 0. And for this one, when counting A is 1, right? So it should be OK 1 at here. Similarly, for OK 1, if input is 0, 0, A is 0, so it should be the state that output is 0 and the last value of A is 0, so it's go to A 0. And for this test, B is 1, right? B is 1. Okay, so it should be state that Z is 1, and so it should be OK what? A is 0, right? Then OK 0 at here, A is 1 at here, so it's OK 1 at here. And this one, OK 1, the last value A is 1, and when counted A is 1 again, so it should be OK 1 at here. Okay, now you can complete this state output table. So you can continue the design after you have got the complete state output table. Okay, but before go to the next step, someone maybe check, okay, maybe check that if I apply the input to the state machine that follow this state output table, so you can check, right? We find the state for each period of clock, okay, and then find out the output, right? That the same as the given condition or not, right? If it yes, it's okay. By the way, someone maybe think one method or one idea, but someone may think with another idea. So someone may get from this state output table which have got 1, 2, 3, 4, 5 steps. That means if you use flip-flop to implement for this state output table, you need at least 3 bits, right, to represent each state. That means you must use at least 3 flip-flop, okay, to implement this state machine. But someone may be think and get 7 state of state output table, and someone get 9 state of state output table. So if you design by using this 9 state, maybe you need 1, 2, 3, 4, right? 4 bit or 4 state variable or 4 flip-flop to implement the circuit. Okay, different, same problem. So to solve the problem, you may need to do state minimization. Okay, this state minimization. Namely, at the beginning, okay, you can think freely, okay, by your own idea. And when you get this state output table completely, you must consider which state have got the same output and the same next state for every input condition. Namely, you must find the equivalent state. Okay, equivalent state. Okay, the state that have got the same output and next state for any input combination. Okay, so now, for example, this one. State what? Maybe this one, state OK 00 and OK A0. Same next state, same next state, same next state, same next state, and same output. That means these two states are equivalent together. Okay, you can delete one of them, okay, to reduce to only one state. Okay, you can merge them together. So now there is no OK A0. That means everywhere that have got OK A0, you must change to OK 00. Okay, for example. And the state also OK A1 and OK 11. Okay, same next state, same next state, same next state, same next state, and same output. So you can remove one of them. And now you get 5 states at the previous state output table. About this one, for this one also you can reduce number of states by observe which states are equivalent together. For example, this state A110, AE11, right? Same next state and same output. So you can reduce number of state, right? Maybe I delete this one, and don't forget to change the name. To change the name, AE10 to be A110. It will replace AE10 and we change to A110. Okay. Change it here, change it here, and then you consider which state are equivalent together. Get this state, right? This state and this state, right? Same next state, same next state, same next state, same next state, and same output. So you can remove one of these and maybe change the name AE01 to A001. 01, this one, right? What else? Okay, maybe. And sorry, 0 right here. And what else? That may be equivalent together. Oh, this state, right? This state and this state. Okay, equivalent together. Same next state and same output. So maybe I delete this one and change the name to OK11. Okay, for example. And after that, okay, let me change the name. OK11 and here. This one, OK11 and here. What else? This state, right? This state have the same output. Sorry, same next state and same output. So you can remove one of these. And finally, you have got 5 states also. After you use equivalent state to reduce number of states. Okay. Okay now. After you have got state output table. Okay. The next one, you must change the state name to binary number to do the design, maybe by using KMap or something, okay, to derive output equation and excitation equation. Okay, now this step is called state assignment. Okay. To assign specific binary code to each state name. Okay. The basic concept is very easy, right? You can assign any binary code to the state. Just the state, each state might have got different binary code. That's all. Okay. For example, because there are 5 states, right? The simplest one is you define by binary counting order. Remember, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and 1, 0, 0, for example. And someone maybe use this decomposed state assignment. This decomposed you define some meaning to each bit. For example, 0, 0, 0 for initial state. Okay, and when it go to some state that not initial, this bit will be 1. Okay. And the state that output is 1, namely state okay, this bit is 1. and this bit Q3 maybe show the value of A at the last clock tick, right? A is 0 at the last clock tick. A is 1 at the last clock tick, something like this. Okay. And maybe use this one hot. If you have 5 states, this state assignment will use 5 bits. Only 1 bit is 1 hot. That means only 1 bit is active. So if this bit active, that means it's state 1. If this bit active, state 2. If this bit active, state 3. If the bit active, state 4. And if the bit active, state 5, for example. Or if you want the integer state to be 0, 0, so maybe you use this one. Almost 1 hot. Integer state is 0, 0, 0. And the left state have 1 bit active only. So you need 4 bit for 5 state, for example. You can use any state assignment. Everyone is okay. It work. But the difference is number of logic gate that you maybe implement circuit F and G. Okay, it's different. The detail for the circuit connection for F and G, but you get the same final output, okay, that you want. Okay, anyway, for this example, we will use this state assignment, decomposed state assignment. And one thing that you should know, if I use this one, that means I use 3 bit, right? 3 bit for 5 state. But for 5 state, 5 state, right? But 3 bit can represent 0, 0 to 1, 1, 1, right? Can have 8, okay, pattern, 8 possibility that it can be. But you use only 5. That means there are 3 binary code that you don't use. Okay, this is called unused state. Okay, unused state. Okay. Now, okay, let you decide. After you determine the state assignment for each state. In this example, let initial state, okay, is represented by 0, 0, 0, okay, for variable q1, q2, and q3. And for a0 is 1, 0, 0, a1 is 1, 0, 1, ok0 is 1, 1, 0, ok1 is 1, 1, 1. That means in the table, you must replace, for example, because a0, okay, you use 1, 0, 0, right, to define this a0 state. So everywhere in the table that is a0, okay, you must change to 1, 0, 0, 1, 0, 0, okay, just change the name to binary code, okay, 1, 0, 0, okay. For a1 also change to 1, 0, 1, okay, 0, 1, 1, 0, okay, 1 is 1, 1, 1, okay. After you change all state name to binary code, you will get transition table. Namely, the value in this one is Q star. Namely, if you consider the structure, You use 3 state variable, that means you have got 3 flip-flop, right? This transition output table is show relationship between output of flip-flop Q1, Q2, Q3, and input of circuit F, namely AB, right? And Q1, Q2, Q3 that feedback from output of the flip-flop is what? And input A, B from external circuit. Okay, this transition, okay, table show the relationship that when clock tick, right? When clock tick, the next value of flip-flop or Q star, Q1 star, Q2 star, Q3 star, change to this value, okay, based on the present state or current state and the input, okay, when clock tick. So now, if you want to design circuit F, that means you should know what? You should know the output, right, of circuit F. Because output of circuit F will apply to input of flip-flop. So it is the same signal, okay? This is excitation signal, right? Excitation signal. And it's based on type of flip-flop that you use in the circuit. If you use D flip-flop, it's easy, right? Because Q star same as value of D. But if you use JK flip-flop, so that means you the flip-flop have two input, right? Two input. So circuit F must have got what? 6 output, right? To apply the signal to JK flip-flop this. Okay, these 3 JK flip-flop. Okay. So how about this example? This example I will show you to design by using both D flip-flop and JK flip-flop. Okay, let's go. For that, you should know something like this. If you use D flip-flop, and if you want, for example, this one is D flip-flop, right? D flip-flop, and because Q may be 0, right? When clock tick, change to Q star. It may be changed from 0 to 0, or 0 to 1, or 1 to 0, or 1 to 1, right? This is 4 possibility when clock tick. If you want, if the current state is 0, when clock tick, you want Q star to be 0 again, that means you must D to be 0, right? This is input D. That the value should be 0, right? And if you want 0 to 1, Q change 0 to 1, that means when clock tick, input D should be 1, right? So this should be 1. And if you want Q change to 0 when clock tick, that means you must apply 0 at here, right? So it should be 0 at here. And if you want Q change 1 to 1, that means when clock tick, it should be 1 at here, right? Okay, so based on this, we see that what? D is the same as Q star. Okay, so if you write in the table, you get something like this, right? Value of D same as value of Q star, okay, for the next state. And how about JK flip-flop? For JK flip-flop, for JK flip-flop, again, if you want output Q, change to Q star, maybe form 0 to 0, 0 to 1, 1 to 0, or 1 to 1. Okay, 4 possibility. How about input JK? JK, if you want output Q, change from 0 to 0. It may be what? It may be hold mode, right? 0, 0, right? Maybe 0, 0. Or maybe reset, right? For reset is J is 0, K is 1, right? J is 0, K is 1. So, if you consider these two cases together, J what? J is 0, right? K can be 0 or 1, right? If the right one, okay, attached to this 0. So, you can consider that J is 0, K is don't care. Okay, K can be both 0 or 1. Okay, okay. Similarly, how about this? 0 to 1. You may consider it as toggle 1 1 or set, right? Set is 1 0, right? J is 1, K is 0. So if you combine these two cases, you will get 1 and don't care, right? And 1 to 0 maybe toggle or reset. Reset K is 1, J is 0, right? When you combine these two cases, it's be don't care 1, right? J can be 1 or 0, so it's don't care, K is 1. Don't care 1. 1 to 1 may be whole 0, 0 or set. J is 1, K is 0, so it's don't care 0. So you can summarize to this table. Sometimes it's called application table to show that the applied signal to the input should be some value, okay, based on this one. And one more example, how about T flip-flop? T flip-flop with enable Q. Again, Q will be changed from 0 to 0, 0 to 1, 1 to 0, and 1 to 1. Now it's changed or not based on the value of enable, right? Enable. 0 to 0, enable is 0, right? Not change. 0 to 1 is toggle, right? Enable should be 1, 1 to 0 also should be 1, 1 to 1 also. And should be 0, right? Not change. Okay, this is relationship between input and state change of T flip-flop with enable. So the application table of this one is this. Okay, now let's go to the next step. The next step, you want to generate this table, excitation table. Namely, now for transition table, you know relationship between output of flip-flop and input of circuit F, right? Now, I want to know output of F, right? And input of F. Namely, output of F is input of flip-flop, right? So from this transition table, I want to generate excitation table to show relationship between output of F and input of circuit F. Okay, what should I do? Okay, when I use D flip-flop, it's very easy, right? If I use D flip-flop, the value of D same as Q. That means if Q star is 1, 0, 0, for Q1 star, Q2 star, Q3 star, that means D1, D2, D3 also must be 1, 0, 0, right? When clock tick, read value to make Q star to be 1, 0, 0. Okay? Or if you want Q1, Q2, Q3 star is 1, 0, 0. That means input D1, D2, D3 must be 1, 0, 0 at the clock tick, right? Okay, to make Q1 star, Q2 star, Q3 star to be 1, 1, 0 also. Okay, so you have got the same result. Okay, for another case, namely to just copy this one. And the problem is, how about next state of undo state? Okay, you use this 5 state, right? And you have got 3 undo state. How about next state of this one? How about of this one? Okay, you may define next state by using these two methods. The first one, assume this is 5 state, okay, that you use, and 3 undo state. Someone define the next state of undo state to be some use state. For example, go to initial, something like this. That means if the circuit go to undo state by something, maybe some noise, or at the beginning when you apply the power to the circuit, maybe it start at undo state. It's also possible. Anyway, if you wait one clock tick, okay, you should go back to initial state, okay, or some normal state that you use. Okay, this method is called minimalist. Okay, minimalist. Okay. By the way, if you treat the next state of undo state as don't care, do something, don't care, it's also possible, right? And when you determine the circuit F by using K-map to find out the equation, if that K-map you select D, that means it will be 1, right? And the bit that you don't select, you give 0, right? Result, something like that. Okay. For this case, you get maybe small number of logic gate, okay, to implement the circuit F. So for this method, it's called minimal. Namely, number of logic gate, okay, maybe smaller than the first one, okay, minimal risk. Anyway, after you get the equation for circuit F, okay, to implement the state machine, you must check that the next state of undo state, okay, can go to the normal state or not. Namely, 1, 2, 3, 4, 5 for normal state, and 1, 2, 3 for next state. Okay, after you obtain the final equation for excitation equation or transition equation, something like that, you should check the next state for undo state. If it go to this one, If this one go to this one, or this one go to this one, it's okay, because it can back to normal state. Or this state, and next state is this one to this one, this one to this one. It's also okay, because you have to wait for clock tick 1, clock tick 2, clock tick, or 3 clock tick. It can back to normal state. But if the next state of undo state, maybe something like this, go to something like this, namely is if it cannot back to normal state, it's not okay, because your circuit maybe if lost to undo state, it cannot be to normal state. Something like sometimes maybe you're using your computer or smartphone, right? If go to some undo state, that means maybe you cannot do nothing. Okay, you press any keyboard or moving mouse, but nothing happen. Okay, so you must restart your computer or smartphone again. Okay, this is the situation that you should uh, be careful. Okay, for this. Okay, so in this case, I show you for both cases. Okay, minimalist and minimal cost for D flip-flop and JK flip-flop. Okay, at first, I show you for the more normal state at first. For D flip-flop, okay, just copy this one, right, to this one. For JK flip-flop, for example, if you want Q1, okay, is 0 to be Q1 star of 1. That means your JK for flip-flop Q1 is J1 K1 should be 1, don't care, right? 0 to 1, right? 0 to 1. Maybe toggle, right? For JK or set 1, 0. So it's 1, don't care for J1 K1. Okay, for example. For another value also, okay, you can fill the value of JK. And for the next state of undo state, if you use minimal risk, for example, you may define the next state of undo state is 0, 0. So the value of D1, D2, D3 also 0, 0, 0, 0. But for minimal cost, maybe you define next state of undo state as don't care. That means D1, D2, D3 also don't care. Okay, for example, something like this. For JK flip-flop also. So based on this one, for D flip-flop, okay, for minimal risk, if next state of undo state is 0, 0, okay, you get K-map like this. And for minimal cost, you consider binary code of next state of undo state as don't care, and you get K-map like this. So from K-map, you will get excitation equation, okay, for minimal risk and minimal cost. Follow this. And for the output also, for minimal risk, someone may define 0, 0 for undo state. When someone for minimal cost, maybe don't care. Okay? And when you write K-map for output, you get equation for both cases, minimal risk and minimal cost. After that, you when you know equation uh, for skid F or excitation equation, and for skid G is output equation. So now you can implement the state machine by connect the circuit from this excitation equation and output equation. Okay, that's all. And for TK flip-flop also, okay, I show you two cases for minimal risk and minimal cost. Okay, after that you get you use this K-map, okay, to find excitation equation and output equation. So you get this excitation equation for J1, J2, J3, and K1, K2, K3 for minimal risk and minimal cost, and output Z for the both case. Okay. After that, you just implement the circuit for this excitation equation and output equation. Okay, that's all. Okay, for the design. Okay, and for the next example, I'll show you next lecture. Okay, that's all for today.